Okay, so let's see here. We got to find the magnitude of the induced EMF during a time interval where this magnetic field here of 22 Tesla is going away, drops down to 0. Okay, so the induced EMF goes as delta phi b over delta t. Now in this case, delta phi b, well, sorry, I forgot the n. Delta phi b is going to be based on delta b times a times cosine theta, because the area of the loop's not changing and the angle that the loop makes with the magnetic field's not changing. It's just the external field that's changing. Okay, divided by delta t. Okay, so that's, let's see, n is just one turn. Change in the magnetic field, it goes from 35 Tesla pointing into the page to 22 Tesla pointing out of the page. So if into the page is positive, then out of the page has to be negative, right? That's a change of 57 Tesla. We got to be careful about that part. The area, it's just a square, so I take the side squared, and then the cosine theta term is just 1. And then we divide by the time interval, which is 0.15 seconds. So that gives us 23.75 volts, which we round off to 24 volts. Now, for part B, we need to find the direction of the induced field. Okay, so the flux in the loop is into the page and decreasing. At least for the first part of the change. For the second part of the change, you could say that it's out of the page and increasing up to 22. Right? This takes it from 35 down to 0, and this takes it from 0 to 22. But either way, the induced field to oppose this change is into the page. No matter which of these two cases you pick, the induced field points into the page to oppose the change. Now for part C, the induced current, if the field of this loop points into the page, then the right-hand rule tells us that the induced current has to flow around like this. If you point your thumb in the direction of this induced field and you curl your fingers around it, then of your right hand, you're going to get a clockwise current.